Okay. Yeah, this problem is called deforestation. I think my zoom is a bit off. Okay. Yeah, so this is the deforestation problem. Yeah, okay, so I guess the first sample input is covered. Yeah, so there's n trees, right, on a number line, and the ith tree is at some location on the number line. And then there's a bunch of constraints. So inside a range, there needs to be at least ti trees, right? And Farmer John wants to cut as many trees as possible, right? So I guess I'll just draw a very simple example. So if you have 3 trees and constraint ti equals 2, then this range has to have at least 3 trees inside, right? And then the goal is to find the maximum number of trees Farmer John can cut down. So in this case, Farmer John can just cut this one down. So then the answer is equal to 1, right? Yeah. And there are some cases here. Yeah. Yeah, there's, wait, sorry. Yeah, I think this is the same case. Yeah, these are just some additional cases. Yeah. Yeah, I guess I can draw like another case that's maybe more reasonable. So something like this and this. Yeah, yeah. Um, so yeah, if ti is equal to 2 here, ti is equal to 2 here, then you can cut this tree, and the answer will be 2, right? Yeah. Yeah, and just a reminder, we have kind of the usual constraint, n is up to 10 to the 5. So we might want something that's like of n log n, right? Yeah, and the subtasks, one of them is nk up to 16. Other one is up to 1000, so maybe something n squared. And then the other one is kind of interesting. It's basically, you need to have at least 1 tree inside each range. And then the last one is no additional constraints, right? So looking at the problem, we see like the coordinates are from -10 to the 9 up to 10 to the 9 like of everything, right? So maybe this will be something like, this might be -10 to the 8th, 10 to the 6th, and then maybe this is 1 and this is 2, right? But we only care about these values, right? So we can do index compression, right? So we can transform this input, for example, to like this range is from 1 to 4, and then this is 2, and then this is 3, right? So we can do index compression. So then after we do index compression, all the coordinates are up to 2n, right? Yeah. So there's this stuff with like -10 to the 9 up to 10 to the 9. So you don't have to actually worry about these. You can just index compress and assume all the coordinates are up to 2 times n, right? Yeah. Um, yeah. So I guess like this case is brute force, right? There's 2 to the 16 ways, um, 2 to the n or up to 2 to the 16 ways to cut trees. So this will be like k times 2 to the n. Um, yeah. So this is the brute force one. So let's look at, so maybe this one is like n squared, but let's look at this case, this subtask, which is inputs 6 to 7. because that might give us useful intuition, right? So what subtask 6 to 7 is that uh, each each range must have at least one tree, right? So each range must have at least one tree. So I'll move to OneNote. So this is problem 2. So one of the subtasks, sorry, one of the subtasks um, is ti is equal to 1 for all I, right? So remember our goal is to maximize number of cuts. Yeah, so you can view it this way. Equivalent way of viewing it is also equivalent to like minimize the number of trees that you keep. So that all these constraints are still satisfied. So you can look at an example. So I'm just going to talk about it from this perspective, or you minimize the number of trees. So if you have these two ranges, yeah, maybe you have something here, you have something here, and you have something here. You can decide to keep this one, right? Yeah. And I can do another case. Maybe you have like there's one case, there's another case. Of this one and this one. Um, so yeah, you want to keep this one because each range has to have at least one tree, right? Um, so we can do the following. So we can try processing things from left to right, and then uh, try to see how we can minimize the number of trees, right? So goal, I guess if you think of these as points as segments, is to find min number of points. Sorry. Such that each segment contains a point. Right. So we can go from left to right. Yeah, and one interesting thing about this problem is that it's it's guaranteed that the forest initially satisfies these restrictions. So solution is guaranteed to exist, right? So let's look at this example again, this specific one, right? So I'll just draw it below. So there's a tree here, and there's a tree here, right? So it's always better to keep like between these two things, it's always better to keep this one because it's intersecting with this and it's intersecting with this. So one thing we can try is we can go from left to right. And then once we hit a right endpoint, we can check, yeah, we can check if it already contains a point. Yeah, we can check if it already contains a point. And if it does, then we're done. Otherwise, you include the rightmost point. Right? So the algorithm is go from left to right. And then when we reach a right endpoint of some interval, when we're at a right endpoint, it's always better to pick the rightmost one because that will intersect with more segments in the future, right? Pick latest tree, right? Yeah. So what we can do now is, yeah, we can do some kind of a sweep, right? So yeah, so our events will be like, yeah, yeah. So the events, yeah. So an event is when we go from left to right, we either add a point. So events we either add a point or we reach the right endpoint. I guess I'll just reword this. So when we go from left to right, we either like see a point or we reach a right endpoint. And then when we reach a right endpoint, we can see if there's already any points covering this. And if there's not, then we add the rightmost point. Right? Any questions how this algorithm works? So again, reminder this for ti equal to 1. Yeah, and then maybe you have like another line here, and a point here. And then when you're here, you already see that you have a point, so you don't need to do anything. And then when you're here, there's no point that's included, so then you can include this one. And when you see a point, basically when you're adding the rightmost point, you're looking at the maximum point that's still available. So when you see a point, you can add to a priority queue. And then when you add the rightmost point, you can just like keep track of the latest point that you have, and then remove it from the priority queue. So you use the priority queue to find the rightmost point. Yeah. So that's the idea for ti equal to 1. So that will give you the second to last subtask. And let's go over how to do it for general ti, right? Yeah, so the idea is go from left to right, and when you're at a right endpoint, you want to minimize the number of points you include, so just add the rightmost point that you see. So for general ti, we can do the following. Sorry. So let's say our points are like this. Or let's say a range is like this, another range is like this, points like this. And maybe this has like ti is equal to 3. And then this has ti equal to 3. And this has ti equal to 1, right? So we can still process from left to right. And it's always optimal to pick the points as right as possible, right? So from this endpoint, we pick these 3 points. And then for this endpoint, we see that already 2 points are there. So then we pick this point, right? So we shouldn't, picking this point is better because there's this t equals 1 here, right? And then when we're at this t equals 1, our constraint's already satisfied, right? So the strategy here is to keep going from left to right. And then when you reach your right endpoint, keep adding the rightmost point until your constraint is satisfied. Yeah, so I can write some pseudocode for this. Yeah, so the idea is like, yeah, so basically your events, they're the same thing, see a point, and then reach right endpoint. And when you're seeing a point, when you're going from left to right, you can add to a priority queue. And then when you reach a right endpoint, basically it's like while total number of points less than ti, add biggest point. Right? Yeah, so I'll write some pseudocode for this kind of. Yeah, 1 sec. Yeah. So it's going to look something like this. So you can iterate over the coordinates from 1 to 2n. And then if there are like any points in C, right? So if then you can add C to a priority queue. And then otherwise, like there might be pairs of the form LC that end at C. And then while num points in LC is less than T, like the TI for this thing, um, add largest point from the priority queue. Right? So the question is how can we check if the number of points in this range is less than or equal to T, right? So I guess the brute force way, you can check this in, you can find the number of points inside this range in O of n time, right? Just iterate over all the points. So then, yeah, and then you're going to add something to the priority queue at most n times. So then this will be roughly like O of n squared-ish, which is enough to pass this inputs 3 to 5 case, right? Yeah, so to summarize this n squared algorithm, we're going to speed it up with a minor modification. You go from left to right, and then you process points, and then when you're at a right endpoint, you keep adding the you keep adding the rightmost tree that's available until the constraint is satisfied. Yeah, I'll just summarize what we did up to here. Yeah, so the goal was to maximize the number of cuts. So this is equivalent to minimizing the number of trees. And then our greedy algorithm is to go from left to right. And then when we're at a right endpoint, keep adding the rightmost point until the constraint is satisfied. So here we add points for this first, then we add points for this, and then we check if we add points for this, right? And then basically we go from left to right, see what happened, what events happen at each coordinate. So if there's a tree at C, then you can add it to a priority queue where C is your coordinate. Otherwise, while the constraint is not satisfied, you keep adding the highest valued thing, right? Any questions? Yeah. So we'll talk about how to speed this up. So there's a data structure called a binary index tree. Yeah, so you can, yeah, it's a good thing to learn, but you can feel free to look it up after. But I'll just say what you can do is you can maintain an array, and then you can do operations of this form. So add AI plus equals X, and then query the sum of a range, right? And both of these operations can be done in log n time. Yeah, so I suggest looking this up. The implementation is actually very short. It's like 2 for loops. But essentially, instead of like iterating over all the points, all the trees to find the total number of points in the range, what you can do is you can, whenever you add a tree, you can add them to a binary index tree, right? So let's say these are your trees, basically adding +1 at a location. And then whenever you want to check if the number of points is less than Ti, this is a range query, right? So this is L and C. You do a range sum query, right? Yeah. So this algorithm naively is O of n, but if you do the binary index tree, it'll be this part will be log. This querying will be log n. So the time complexity will be like linear in n and k times the log factor. Any questions about this problem? Yeah, I think there's also a way to do it without a binary index tree. It's kind of complicated. I think this may be a simpler one that I'm aware of. But I think if you know policy-based data structures, like sorry, like ordered set, those kinds of things also work here. Okay, so I'll go over the third.